So we left off on Friday that talking about heterogeneous equilibrium. And so remember, in heterogeneous equilibria, we had the situation where not all of our species were in the same phase. So maybe we had some solid and some liquid stuff together, or solid and gas. And we had to figure out what to do with that and how to write our equilibrium expression for it. Remember, for any equilibrium constant expression, we're always going to leave out pure liquids and solids. The reason we do that is because their concentrations don't change. If I have pure water and I take it away a little bit, I still have pure water. The concentration of that water hasn't changed, even if the volume has. Same with solids. If I have a solid and I take away a little bit, the concentration of that solid hasn't changed. And so we don't need it in our equilibrium expression. So we have a couple of examples, example 5 and 6, that deal with writing equilibria for these heterogeneous reactions. And let's take a quick look. So hopefully you can see that. So we're going to write Kc and Kp, if it needs a Kp, for these heterogeneous systems. Right? Well, the first thing I'm going to do is, if we look at part A here, we're going to cross out the ones that we don't necessarily need in our equilibrium expression. And is that our reactant or our products? Which one of those do we not need?
Product.
So remember, we ignore solids and pure liquids. And so this solid here, we don't really need him when we write our equilibrium expression. And so Kc, remember, is products over reactants. There's no reactant, so it's just product times product in H3, H2SE. Is that it?
No.
What do I need?
A 2 on NH3.
Yeah, remember, for our equilibrium expressions, we use those coefficients as powers. And so we need to square the concentration of NH3. Since we ignored the solid ammonium selenide, we have just gases left over. And so we can also write a Kp expression for A here. And so Kp is just the pressure of each gas. So the pressure of ammonia squared times the pressure of this hydrogen selenide. Okay. Again, we can only write Kp's if all of the components are gases. Right? All of the components that appear in Kc. Again, here we ignored solids, and so we can write the two gases left over as either concentrations or as pressures. For B, do we ignore any of these three chemical species?
The solid.
That's it. So we don't have to worry about this silver chloride, and so we can write our Kc as just the concentration of silver plus. Be sure when you write concentrations for ions that you include their charge, just so we know whether it's an ion or whether it's the atom. Right? So the concentration of silver plus times the concentration of Cl minus. We don't need any powers because their coefficients are 1. And we can't write a Kp expression because they're not gases. Okay. This last one, part C. Can we ignore anything here?
The solid and the liquid.
The solid and the liquid we can ignore in our equilibrium expression. And so Kc, now remember it's products over reactants. There's nothing in the products, so we just have a 1 up there. And then there's going to be over our reactants, Cl2. Now there's a coefficient of 6 in front of that Cl2, so it's 1 over the concentration of Cl2 to the 6th power. Chlorine's a gas, so we can also write a Kp expression 1 over the pressure of Cl2 to the 6th power. So this is not all that different from the ones we did on Friday. It's just being sure that we take into account the fact that we can omit those solids and pure liquids. Right. The reason we say pure liquids, just as a quick aside here, right? Aqueous, that's also a liquid. It's something dissolved in water. It's still in the liquid phase, but it's not a pure liquid like PCl3 is in this example. Any questions writing those equilibrium constants? All right. Hearing none, let's move on to example 6. We have an equilibrium between calcium carbonate and calcium oxide plus CO2. And so it gives us a temperature, and it gives us a pressure of one of the products, CO2. It gives us the pressure. And so we're going to calculate KT and KC for the reaction of this temperature. Well, if we write out our Kp expression, since that's what it asks for first, Kp is equal to, well, products of reactants. Calcium oxide, that's a solid, we don't need it. Calcium carbonate, that's a solid, we don't need it. It's just equal to the pressure of CO2. And so Kp is equal to 0.236 at 800 degrees C. Pretty straightforward. Now, to find Kc, we need to know that relationship between Kc and Kp, and that has to do something with the ideal gas law, if you remember from Friday. And so that relationship is Kp equals Kc times RT raised to the power of delta N. So we have Kp 0.236. Remember, no units on equilibrium constants, and so even though that started out as an atmosphere unit, we don't have any units on our equilibrium constants. So 0.236, and we're solving for Kc. Now, R, again, we need the gas law R, 0.821 liters, atmospheres per mole Kelvin. And we're going to multiply that by the temperature. Is the temperature 800? No, we have to convert it to Kelvin. So we add 273, so 1073 Kelvin. And then our number of moles of gas. What's delta N for this reaction?
One.
Yeah, it's just 1, right? Number of moles of gas in the products is 1. Number of moles of gas in the reactants is 0. So 1 minus 0 is 1. And so, again, normally we don't write exponents of 1, but I'm going to write it there just so we know that it's 1. And then we just need to rearrange and solve for Kc. 0.236 divided by 1073 divided by 0.0821. We end up with a Kc value of 0.00268. Again, no units on equilibrium constants. Again, not very different from what we did on Friday when we did a practice problem with Kc, Kp conversion. We just have to remember to ignore the solids in our reaction. All right, so moving along, in chapter 13, one of the last things we talked about was those elementary steps and figuring out the elementary steps to a reaction. The reason that we're interested in doing that is because for the rate part of the experiment, calculating the rate law for an elementary step is much easier we don't need to run an experiment. We just need to know that the rate is equal to K times the concentration of the reactant raised to its coefficient, right? That's only true for elementary steps, not true for the overall reaction. But that's one of the reasons why we like to know those elementary steps. So once we have those elementary steps, we can write our equilibrium constant. And so let's say that we have A and B that are in equilibrium with C and D. Again, this is an elementary step. Elementary steps can still be equilibria like this. They don't necessarily have to be, or both of them don't have to be equilibria. It just depends on the reaction. But for example, let's say this is step 1. Right? In step 2, C and D turn into E and F. So this is a 2-step mechanism. What do we call C and D?
Intermediates.
Intermediates, that's right. And so because they're intermediates, they're created in an early step and they're used up in a later step. And so C cancels out, it's on both sides of the arrow. D cancels out, it's on both sides of the arrow. We end up with A plus B in equilibrium with E plus F. Now, if we take a look at the equilibrium constants for these elementary steps, we know that Kc, I'm going to put Kc1 here, is equal to the concentration of C times D divided by the concentration of A times B. And Kc2 is equal to the concentration of E times F over the concentration of C times D. Now our overall K, which I'll just label Kc, okay. Our textbook does use primes, so Kc prime for the first one and Kc double prime for the second one. Either way is fine with me. However you want to do it is A-OK. But then our overall Kc is equal to, well, if we look at our reaction, concentration of E times concentration of F divided by the concentration of A times the concentration of B. Well, that overall reaction is not Kc1 or Kc2, but it's related to those two. Who sees that relationship? It has to do with those intermediates. So for Kc1, I have C and D in the numerator. For Kc2, I have C and D in the denominator. How could I get rid of those?
I mean, don't they just cancel out?
If we do what?
Like ratio, like cross, I don't know. I can't remember the math term.
Yeah, so over here, for our reactions, we just added the reactions together. And if it was on one side of the arrow, it cancels out on the other side of the arrow. But if we just add these, C and D don't cancel. What do we have to do to them?
Multiply.
Yeah, we've got to multiply these two together. And so Kc equals Kc1 times Kc2. And so if I write that out, find my eraser here. C times D over A times B times E F over C D. C cancels, D cancels. I'm left with E times F over A times B. Okay. And so anytime we have some overall reaction that's the sum of two or more reactions, we just have to multiply those equilibrium constants together. So if a reaction is the sum of two or more reactions, multiply K values to get the overall K. All right. So that's elementary steps and elementary steps in equilibrium. And so anytime we have a reaction that's made up of more than one step, we just multiply those equilibrium constants together to get the overall equilibrium constant for a reaction. Any questions about that? Okay. So reversible reactions. This one might seem a little silly. We've been talking about equilibrium where we have a forward reaction and a reverse reaction. And if we have both directions of reaction, aren't they by definition reversible? Yes, they are. And so all of our equilibrium reactions are to some extent reversible. If K is huge, right? If K is huge, then we really favor the products. And if we really favor the products, then it's not truly a reversible reaction, right? It doesn't really want to go back to the reactants at all. And so that equilibrium is not a true equilibrium. It's if K is 1,000,000 or something, we're pretty much going to get all products with no reactants left over. The opposite is true. If K is 1,000,000th, right? If K is very small, then it's going to stay reactants and we're not going to get very much product at all. And so we don't really consider those reversible. It's those in-between numbers, right? K that's close to 1, where we are consider those to be reversible. They can just as easily go in one direction as they go in the other direction. And so for reversible reactions, sometimes it doesn't really matter which way we write it, right? So the one that we saw at the beginning of this chapter, N2O4 in the gas phase, forms a pretty decent equilibrium with 2 molecules of NO2. And this K is not that small. K is equal to 4.63 times 10 to the negative 3. But if we write it the other way, 2 NO2 in the gas phase are in equilibrium with N2O4 in the gas phase. Now, chemically speaking, there's not a whole lot of difference between these two reactions. Right? They're both equilibria, and so they're going back and forth between these two. But the way we think about the equilibrium constant is different. Right? For this reaction on the left, where we start with N2O4 as a product, K is less than 1. And so does this favor the reactants or favor the products? If K is small.
Reactants.
Yeah, this favors the reactants. Okay. And so you can imagine that if we flip it, right? If we flip it, so in other words, it favors N2O4. If we flip it, it's still going to favor N2O4. And so here it must favor the product, which means K has to be greater than 1. But how do we find K, right? Let's look back at our math. The expression for K is the concentration of NO2 squared divided by the concentration of N2O4. Here, K is equal to the concentration of N2O4 divided by the concentration of NO2 squared. How are those two related?
They're reciprocals of each other.
Yeah, these are inverse or reciprocals. Right? And so, let me make this one K prime just so we can keep things straight. So this K prime is equal to 1 over K, right? If this is K, and this is K prime is equal to 1 over K is equal to 1 over 4.63 times 10 to the negative third. And if we do that math, 4.63 times 10 to the negative third, 1 over that, we get 216. So again, it's not a million. It still has a true equilibrium setup. But the relationship between reversible reactions like this are that if we flip the reaction, we take the inverse or the reciprocal of our equilibrium constant. Okay. All right, so let's look at a couple of reactions here, a couple of examples. If we look at ammonia, we have 3 different ways of writing it, right? The only difference between these is where the coefficient of 1 is, right? So in A, the coefficient 1 is in front of the nitrogen. In B, the coefficient 1 is in front of the ammonia. And in C, the coefficient 1 is in front of the hydrogen. And so, we might change these coefficients depending on what we're interested in looking at. This is the first time that we've seen fractional coefficients in this class. I don't know if you saw those a little bit in 123. We talk about it a tiny bit in chapter 6, where we talk about the enthalpy of formation. We see some fractional coefficients, but it is possible, right, to see these fractional coefficients. And if we do the math here, this K for A is equal to the concentration of NH3 squared divided by the concentration of N2 times the concentration of H2 cubed. Let me change colors for B. K for B is equal to concentration of NH3 to the half divided by the concentration, oh, sorry, not a half there. Oops. Times the concentration of N2 to the half times the concentration of H2 to the 3 halves. And then for the last one, K is equal to concentration of NH3 to the 2/3 divided by the concentration of N2 to the 1/3 times the concentration of H2 to the 1st. Okay. And so while these look kind of similar, they're not exactly the same. And so if we look at the first two, if we look at A and B, how do we go from something squared, so ammonia squared, to ammonia to the 1st power? How do we do that? Get rid of a square.
Square.
Take the square root, absolutely. And so if we take the square root of the top, we go from 2nd power to 1st power. If we take the square root of 1st power, we get half power. That works. That's mathematically accurate. If we take the square root of 3rd power, we get 3/2 power. And so it turns out that purple K here, oops, that's not purple. Purple K is equal to the square root of red K. Okay. Another way of thinking about this, from A to B, what do we multiply all those coefficients by?
One over two.
Yeah. From A to B, we multiplied everything by 1/2. And so I'm going to put in parentheses here, times 1/2. Okay. And so purple K is equal to red K raised to the 1/2. That's the same as a square root. And so it's raised to the power of whatever we multiplied by. So for A to C, what we did was we multiplied by 1/3. So blue K is equal to the cube root of red K, or red K raised to the 1/3 power. And so that relationship between those equilibrium constants all has to do with the factor that the equation is multiplied by. And so the new K is related by K to the, I'm going to put raised to the X here, where X is the multiplication factor for the coefficients. Now, again, it's not often that we would want to know a reaction. We wouldn't want whole numbers, but they do exist. The example I gave of thinking about delta H of formation is a good example, where we want to make 1 mole of product. That's our definition for delta HF. And so we would have to have it in terms of B in this example, where we just have 1 mole of ammonia being formed. Okay. All right, so some general rules for writing equilibrium constant expressions. The concentration of the reacting species in the condensed phase are expressed as molarity, right? So condensed phase just means aqueous for us. We're not dealing with pure solids, and we're not dealing with pure liquids, and so the only condensed phase that we have is aqueous. If they're in the gas phase, they can either be in terms of molarity, or we can do it in atmospheres, and so that's why we can write Kc and Kp for gases. For condensed phase, it's Kc only. Right. Second thing to keep in mind, if we have a pure solid, a pure liquid, or a solvent. So solvents are usually pure liquids, but there are odd cases where they may not be. So we're gonna ignore solids as well, solvents as well. But if you run into a problem like that, it will certainly tell you what the solvent is. And so pure solids, pure liquids, and solvents don't appear in equilibrium constant expressions. There's dimensionless quantity, right? That means no units. We've talked about that. And we talked about the fact that because these are dependent on rate, and at the end of chapter 13 in that Clausius-Clapeyron equation, in the Arrhenius equation, we talked about how the rates are very dependent on temperature, and so the equilibrium constant also depends on temperature. Because you have to raise each concentration to the power of the coefficient, you also have to give the balanced equation that you're talking about. So both things are necessary. And just like we talked about for reversible reactions, if it's a sum of reactions, we just multiply the equilibrium constants for each elementary step. Okay. So just trying to wrap it all together, bring it all together here. These five sort of thoughts as we write equilibrium constant expressions. So how, I've talked about how this is related to one another, and the big thing about equilibrium is how the rate of the forward reaction equals the rate of the reverse reaction. And so if we're at equilibrium, Kf for the forward reaction equals Kr for the reverse reaction. Right? Oh, sorry, that's not true. That's not true. I put it here, and I made myself a note, and I ignored it. It's not Kf, it's the rate forward equals the rate reverse. Okay? Those rate constants can be very different from one another, but the rate itself is what's equal. And so if we think about the rate in the forward direction, so rate F, remember your chapter 13 stuff, it's the concentration of the reactants. So let's assume this is an elementary step. Okay. And the rate for the reverse is equal to AB2 times KR. That's why we have to think about this in terms of rates, not in terms of rate constants. Okay. So if we know that these two rates have to be equal to each other, we can do a little bit of algebra here. And we can say that the concentration of A times the concentration of B squared times K for the forward, oops, that should be squared on the outside, not squared on the inside, equals concentration of AB2 times K reverse. If those two rates are equal to one another, then I can write that expression. If I rearrange things and I get all my K's on one side, K forward over K reverse is equal to the concentration of AB2 over the concentration of A times the concentration of B squared. Well, that looks really familiar. Products over reactants raised to their coefficients. This is equal to Kc. And so that relationship between the rates and the equilibrium constant, Kc equals Kf over Kr. So the rates are equivalent and the equilibrium constant is related to the rate constants. Again, that's where the temperature dependence of equilibrium comes from. So how do we know whether or not we're at equilibrium, right? If I just give you a problem with some concentrations and I tell you what the equilibrium constant is, it might be fairly easy to plug it in and see whether or not it matches. But how do we know which direction it's going to shift in order to figure out whether or not we're at equilibrium? That comes into something called the reaction quotient. So this is Q sub C for concentration. There would be a QP if we did it in terms of pressure as well. But this reaction quotient is calculated just like K, but it doesn't have to be at equilibrium, right? The key with K is that it's the equilibrium constant. And so if you don't have equilibrium concentrations, don't plug it into K, but it gets tricky because Q looks a lot like K. And so this is calculated by substituting the initial concentrations, or really at any point in the reaction, of reactants and products into the Kc expression. Okay. So I want to say one quick thing here. It depends on which textbook you're using, but some textbooks use the brackets that we've been using for concentration. They only use brackets if it's at equilibrium. Everywhere else, they just put it in parentheses. Our textbook does not do that. They put brackets around any concentration. And so that's what I'm going to do. But if you go and you look at a Khan Academy video, or you see it somewhere else, and you see the concentrations in parentheses instead of in brackets, that's because brackets are sometimes used only for equilibrium, not for initial concentrations. And so QC is equal to, for our generic reaction, C moles of C, D moles of D, A to the A, B to the B. And again, that looks an awful lot like our K expression, right? And so I'm going to put here that the only difference between Q and K, Q can be calculated at any point in the reaction, right? K can only be calculated when you're at equilibrium. Okay. You cannot calculate K with initial concentrations. You can only calculate K if you're at equilibrium. And so we look at this relationship between Q and K to determine which direction our equilibrium is going to go. And so if Q is less than K, here at the this first example here, then that means that our products are small, our reactants are big. In order to reach K, we have to shift to the products. Here in the middle, QC is equal to KC. Well, if they are exactly the same, then our reaction must already be at equilibrium, right? If our Q value is equal to the equilibrium constant, then we are at equilibrium. And then if QC is greater than KC, that means we have too many products, not enough reactants. We're going to shift to the reactants. Okay. And so Q is helpful in letting us know which direction we need to go in order to reach equilibrium. So let's do a quick example here. So it says at the start of a reaction, like this is our clue that we're going to look for Q, not K. And so at the start of a reaction, we have some concentrations of nitrogen, hydrogen, and ammonia. We have our volume and we have our temperature. We have an equilibrium constant that's 1.2. So Kc is 1.2 at 375 C. So we need to determine whether or not we're at equilibrium, and if not, which direction that reaction is going to go. And so we have to calculate Q. Again, it's just like calculating it's just like calculating K. It's the concentration of the products, 6.42 times 10 to the negative 4 squared, divided by the concentration of the reactants, 0.249 times 3.21 times 10 to the negative 2 cubed. Now, before we even do any math, I want you to just think about this. Our K is greater than 1, and so which side should it favor, reactants or products? It's not much greater than 1, but it is greater.
Products.
Yeah, so it should favor products. I'm going to put slightly here in parentheses since it's just barely greater than 1. Do we have a lot of product? No, we do not have hardly any product, right? And so if we had to take a guess, QC probably is less than KC because it needs to shift to the product. But let's do the math. QC, plug it in. 6.42 times 10 to the negative 4 quantity squared divided by 0.249 times 3.21 times 10 to the negative second quantity cubed. Oops, I did to the 32nd, not to the second. 6.42 10 to the negative 4 squared divided by 0.249 divided by 3.21 10 to the negative 2 quantity cubed. And I got a Q value of 0.5. That does not match my notes. 6.42 times 10.
Dr. Davis, I have a question.
Yes.
Do you have to make these into concentrations since they're in moles?
Yes, you do. Thank you. That's what I forgot to do. Excellent. Yeah, so good point, good point. Here we have moles and we have volume. And so we need to turn these into molarities. So scratch that. QC equals 6.42 times 10 to the negative 4 divided by 3.5 liters. 1.83 times 10 to the negative 4 squared. Yeah, good catch. Thank you for that. 0.0711 times 9.18 to the negative 2 cubed. All right, so let's do this now. We're going to -3. We're going to cube that. So, and I got 0.611. That matches my notes. Yeah, so read the question. Remember, these have to be in concentration. And so if you're given moles and a volume, be sure that you find molarities. So QC less than KC, it will shift to the products. All right. That is a great stopping point for today. Like I said, in lab, we'll pick up with Le Chatelier's principle. And then on Wednesday, we'll finish up some chapter 14 mathematics stuff. Okay.
Thank you.
Yep.
Thank you.
Thank you.
Thank you.
Thank you.
Thanks, Dr. Davis.